So moving to a completely different subject, the 2 hours before we talked about precipitations, their effect on radio communication, and especially measuring precipitation themselves using radar. Now we are going up much higher. Precipitations at our latitudes may go up to 10 kilometers. Above 10 kilometers, you have no clouds at all. In the tropical regions, maybe precipitations may climb up to 15 kilometers. But beyond 50 kilometers, you just have air, though very rarefied air. And for the troposphere, last time we used this equation that n is equal to 1 plus delta n times e to the minus h over capital H, where capital H was about 8.5 kilometers, when this delta n was around 0.0003, or 300 parts per million, the map that your colleague requested. Now it seems that climbing up in the atmosphere, the pressure is decreasing. Gases become very rarefied as you climb up. There are no clouds, no water vapor, no clouds, no water drops beyond, say, 10 or 15 kilometers. In the stratosphere, there are no clouds. What happens as we go up? Since there is no material, there are no gases, there are no water drops, ice crystals, there is no change of the refraction index. But what happens at altitudes above, say, 60 kilometers, H, and say less than approximately 1,000 kilometers, but there is no exact limit to this, we get into the ionosphere. So particles here, they may be molecules, they may be just single atoms, they may be ionized atoms, so having 1 electron more or less. They may be also free electrons in the ionosphere. I may have charged particles. So I have here charged particles. And what happens with charged particles? If I have an electric field, these particles start moving. So if I have a particle that has a charge Q multiplied by the electric field, this gives me a force, a certain electrostatic force. And this force is now equal to the mass of the particle times the acceleration. And this is equal to mass times acceleration is the derivative of v over time. Or written for harmonic fields, this is j omega for the derivation, mass times v. This is now the velocity of our particle. I can derive the velocity of this particle out of the equations when I know the charge of the particle, I know the mass of the particle, I know the electric field applied. So now the velocity v is equal to what? Is equal to charge over j omega mass, charge and mass properties of the particle times electric field. So particles start moving. What do these particles do? They produce a convective current. And this convective current is equal to what? This convective current J is now equal to the density of the particles n, where n has units per cubic meter. so density of the particles, times the charge of the single particle, times its velocity. So if I now combine the equations, this velocity of the particle, I plug it up here, the convective current now is equal to what? The convective current is equal to Q, and Q is Q squared, N over J omega mass here, J omega mass, times electric field. So I have a current that is proportional, convective current, to the, this is proportional to the, convective current is proportional to the electric field, with some constant here calculation. So if I write the Ampere law, curl of, or maybe I can write curl with the cross product. So writing the curl with nabla times H is now equal to what? What is this convective current? This is this one here, plus the displacement current, and the displacement current is J omega. It's almost vacuum, so it's epsilon 0 times E. What is now the effect of this current? I can rewrite this thing once again. So I can rewrite this thing in this way. So having both terms assembled, so let's write it J omega epsilon 0 times. This counts for 1. But since I miss here J omega epsilon 0, I have to add J omega epsilon in the denominator. So J times J is minus sign here, and in the denominator now I have omega squared epsilon 0 mass. In the numerator I have Q squared N, and all this is times the electric field, the applied electric field. I hope I did this correctly. Let me check. So J times J gives minus 1, omega epsilon 0, omega squared mass. So I can now say that the actual permittivity is different, that I have a relative permittivity, and the relative permittivity is this bracket here. So this is epsilon relative. I can write now epsilon relative, the relative permittivity of space. This is now the square, not yet. There will be a square root, but not yet, I was too fast. 1 minus here, Q squared, charge of the particle squared, density of the particles per cubic meter, frequency omega squared, epsilon 0, mass of the particle. What is interesting here is that this relative permittivity is actually less than 1. Already this is interesting, but it actually does happen. It does happen that it's less than 1. And also the refractive index of the ionosphere now is square root of the relative permittivity, is now square root of 1 minus Q squared N omega squared epsilon 0 mass. Now you see that strange things may happen here. Epsilon relative, the relative permittivity may get negative. It may happen. May happen negative. Also, where it may happen negative, at very low frequencies. At very low frequencies, this fraction becomes large, and 1 minus something large may get negative. Also, the refraction index may get imaginary. imaginary refraction index means no propagation. So now it makes sense to actually simplify the quantities using this equation, because we are going to use them much in this hour. We want to simplify these quantities and say find a new description for them, something simplify in some way. So I would rewrite this equation. So 1 minus for the relative permittivity, 1 minus q squared n over omega squared epsilon 0 mass. I would prefer to rewrite this thing as 1 minus frequency. I leave it as it is, where it is the frequency, but all the other constant I write this as an omega, as the plasma frequency squared, where the plasma frequency now is the square root of what? Of q squared n over epsilon 0 mass. In this way, it's much easier to deal with all further explanation. Dealing with the plasma frequencies, because here these quantities I may have a mess. I may have particles of different mass, particles of different charges, and so on. But something I should point out here immediately. That electrons, in the ionosphere, I also have free electrons. Free electrons have a very small mass compared to all other particles. Electrons are about 2,000 times lighter than protons, the next larger particle, the next heavier particle. So it makes sense to only consider electrons here. So I have here the charge of an electron squared. I have the density of electrons, epsilon 0, and I have mass of the electron here. Because the mass of the electron, as I said, is approximately mass of the proton, the next heavier particle, divided by 2000. So electrons are much lighter than protons, so they are going to have far the largest contribution to the convective current is going to be given by the electrons. In fact, what I'm actually interested in, I'm not interested in the whole ionosphere, I'm interested in the so-called electronosphere. Just how many electrons do I have in the ionosphere? And I know what are the quantities now I have here. The quantities I have, the mass of the electron is approximately 9.1 times 10 to the minus 31 kilograms, and the charge of an electron is minus 1.6 times 10 to the minus 19 amp seconds. And this is now the exact value here is now also the definition of the ampere unit of measurement. So I know these figures. I know what epsilon 0 is. I only need to know the concentration of the electrons. How many electrons are out there in free space? To see where do these effects take place, where does this omega p take place? Or I also use here conventional frequencies. Say frequently I write the plasma frequencies. I write this ratio as with conventional frequency 1 minus frequency, plasma frequency divided by frequency squared, where I just divide by 2 pi up and down. So the plasma frequency is now approximately, for electrons only, I have 2 pi in front, 2 pi squared in the denominator, epsilon 0, mass of an electron. Up I have q of an electron squared, concentration of electrons per cubic meter. how many electrons, free electrons per cubic meter do I have? And the altitudes when this happens and the densities of electrons are very small over there. So if I try to make a drawing, yeah. Say I start 10 to the 9th power, 10 to the 10th power, 10 to the 11th power, 10 to the 12th power. This is concentration of electrons per cubic meter. Meter to the -3. And if I draw here altitude, 100, 200, 300, 400, 500, 600. Altitude in kilometers. Where do these things happen? Very little happens at low altitudes because below 100 kilometers, the air density is still significant. There are many collisions of these charged particles. There are many recombination of charged particles, plus and minus ions recombine. So I may have some very weak peak here. I have a much stronger peak here. But the strongest things happen up here during daylight. And these ionospheric layers, when physicists first described them, these ionospheric layers, say you have at perhaps 80 kilometers, the layer D, you have at 120 kilometers, the layer E. I have layers F1 at 250 kilometers, and I have another maximum at layer F2, capital letter F, capital letter F1, capital letter 2, at around 250 kilometers, around 400 kilometers. What does this mean in practice? In practice means that the International Space Station is flying over here. So if I draw here the International Space Station is flying at around 350 kilometers. For any practical reasons, these altitudes are, for us, simple observers, are complete vacuum. They are not that good vacuum. These 10 to the 12 electrons per cubic meter, what does that mean? It means that the International Space Station is flying in an acid. Though rarefied, but this is an acid, plasma made of electron. You know that acids work in this way that they form free electrons. And this is acid. And you have to be very careful what kind of metals are you going to build your space station so that it doesn't get eaten off by the acid it's flying in. Though this acid is very rarefied, but observations say on the space shuttle were that the nose of the space shuttle, the point, the tip that was flying into this acid, actually was eaten about 1 millimeter per week. This is an acid. It's not vacuum. Further, when we go further up in space, there is much less acid available. So this is very rarefied atmosphere. And this was during the day. During the night, things go a little bit different. During night, the maximum concentration is somewhere lower, and these lower layers disappear altogether. So lower layers at night are gone completely. Lower layers go completely, and these two layers, F1 and F2, join in a single layer F at around 300 kilometers at night. Because all these layers are caused by short waves, say UV, X-ray radiation from the sun. When at night the sun is gone, we are in the Earth's shadow, some electrons do stay here. Especially the recombination time of electrons in the higher layers are very low, because here the atmosphere is very rarefied. While lower layers, where you have lots of collisions with neutral parts, lots of collisions with other ions, these are gone completely at night. So this is our actual situation of the ionosphere. What can we count now on this ionosphere? At night, the concentration of the electrons in the F layer is about 10 times smaller than the concentration during day. So during day, we have a plasma frequency of, say, around 12 megahertz. But this changes very much on the solar activity. Now, it's very high with the high solar activity, with the lots of solar flares we have right now. And since the concentration changes 10 times, the result during night is perhaps an F plasma, maximum value of plasma, of around 4 megahertz. Now we know the frequencies where we can expect some effect from the ionosphere. From the ionosphere in the higher layers, in the F layer, or in the two F layers here, we mainly have refraction. Because we actually changed the refraction index here. We do have refraction in the higher layers. While in the lower layers, we have collisions here. And when the particle collides with other particles, it moves its momentum to other particles, it gives its momentum to other particles, therefore it loses energies, so here we have additional signal loss. These regions are lossy, low regions are introduce loss, while high regions in the ionosphere introduce refraction. So these frequencies are known. These frequencies, okay, they are maybe 4 megahertz for normal solar activity. They are always is the sun behind. The sun is generating all these charged particles. During day 12 megahertz, during night 4 megahertz. This figure may go quite up with an active sun with lots of solar flares. So it's not something, some fixed figure I can draw on the board here. It's something that's changing all of the time. How can we use these things for radio communication? Okay. We usually don't like loss, signal attenuation. We don't like to talk about that, but even that plays a role. We want to establish long-range radio contacts. Say we have our Earth here. Here is the center of the Earth. And we want to make, so this is the radius of the Earth. And at a certain height, I have the ionosphere. This height is, say, around 300 kilometers, just to give you an idea. And up here, I have the ionosphere. The ionosphere does not have a strict limit where it changes. The ionosphere goes all the way up in free space. So, but it's less dense than its lower altitude. So these lower altitudes are maybe perhaps the most interesting for us. So what I can think of, I can think of a radio link that originates from this station, goes straight to the ionosphere. There is almost no refraction here. Then in the ionosphere, I have refraction. and I can go back down to the ground to this station here. So I transmit to the horizon. Also here I transmit to the horizon. This is the radius of the Earth. This is also radius of the Earth. What is now this distance covered? Distance here or distance here? They are identical. Here, in fact, with this refraction of the signal, I get total reflection. I may get total reflection at some particular frequencies. What is now the geometry? How far can I get with this mechanism? Total reflection because the ray is bending back to the ground due to refraction, due to the changing refractive index of the ionosphere. What distance can I cover with this? So now, if I write down the equations of the triangle, so r of the Earth plus h squared is equal to the Pythagorean theorem, d squared plus r of the Earth squared. But this thing here is r of the Earth squared plus 2 times h r of Earth plus h squared. So if I try to solve this equation, these two cancel out perfectly. And just to simplify my life, I may neglect this term here. H squared is much smaller than twice h r the Earth, because h is 300 kilometers, so h is in the range of 300 kilometers, and r of the Earth is 6,378 kilometers. So that term is quite small. So my simplification now is that the distance covered in one hop over the ionosphere, distance covered in one hop of the ionosphere is now square root of 2 times h times radius of the Earth. How far can I get now? I can calculate this. This is 2 times h is 300, and this is 738,387. All gets kilometers squared, so it will be in kilometers the final result. So I have here 600 times 6,000. 600 squared is about 600. Square root is about 600. A little bit more than 10 is a little bit more than 3. So in place, so 600 times 3 is about 1,800 kilometers. Maybe I have the exact figure calculated somewhere. Otherwise, I could take the calculator. Maybe I have the figure. I hope for the same example. Yes, it's about around 2,000 kilometers. It's 600 times square root of a little bit more than 10 is around 2,000 kilometers. So 2,000 kilometers, one hop, I can make a journey of 4,000 kilometers. I may even have a reflection again of the surface of the Earth. One additional total reflection, so refraction that turns into total reflection. So this, I have a reflection here, and then I have again total reflection here due to the refraction in the ionosphere. I even can get to a multiple of this distance. I can reach practically the whole Earth if the ionosphere is in the correct condition to support this operation. Up to which frequency I can go here? Yes, it depends on what n do I need here. What the n minimum here is required to support this, this operation. And I can draw here the refraction law of reflection here if I had just a total reflection on simple boundary. So if I draw this, I have n over, here I have 1, and I have a ray coming in here. And I want to have it horizontal. So here I have theta, and here I have pi half. If I now rewrite the law of refraction, so sine of theta of the incident theta is equal now to n if I redraw the refraction law. So I can calculate what n do I need from sine theta. And where is theta? Theta is this angle here. Theta on this picture. So I see which quantities do I have here. I need sine theta. Sine theta, you see that sine theta is now here r of the Earth. This is this side here, divided by this side here, r of the Earth plus h. This is the refractive index I can get here. I can get this refractive index only up to a particular frequency. Beyond that frequency, I can no longer get so let me rewrite this now. So refractive index. I should make some space on the board because I don't have any more space here. So we were left here. So our refractive index is now r of the Earth over r of the Earth plus h. And this is equal on the other side to the square root of 1 minus f plasma squared over f plasma over f squared over frequency squared. Now let's try to solve this equation. So I have to make a square. R Earth squared R Earth plus h squared is equal to 1 minus f plasma squared over f squared. If I pull this one on this side, and if I revert the signs, I have r Earth plus h squared minus r Earth squared. If I put it in and flip the sign, divided by r Earth plus h squared is equal to f plasma squared over f squared. On this side, simplifying on the other side, r Earth cancels out, so it's 2 times h times r Earth plus h squared divided by r Earth plus h squared. It all turns out that now I have a fixed ratio that I could, just for simplification, I could simplify this. I say this is around r Earth, and this is also r Earth is approximately 2h, neglecting this one, and I have R Earth in the denominator, cancelling 1 R Earth down here. It's approximately this value. So F now, the maximum frequency we can use, this is also called maximum usable frequency. It's now F plasma times square root of R Earth over 2H. And now plugging in the correct values, so R Earth 6,300, 2 twice H is 600. If I calculated everything correctly, this is about 3.3 times F plasma. So I can get up to frequencies, perhaps, here during the day, the maximum usable frequency may be in the range of 40 megahertz. Up to 40 megahertz, I should establish such connections as given here. It's not particularly high. It should be during daylight. Also during night, these things go slower. During night, these things go 3 times slower. During night, the maximum usable frequency is perhaps just 13 megahertz. Changes a lot from day to night, the maximum usable frequency. Further, I should not forget that on the light side of the Earth, I also have this intermediate D and E layers. D and E, while this layer was the F layer of the ionosphere, or both F layers up here. What does that mean? That means that I have loss here, and I have loss up here. Signal loss I have. Because of attenuation, and also attenuation, we didn't make any derivation here, but also the attenuation in the ionosphere is proportional to the frequency. We don't have the time to do that today. So what does that mean? This attenuation, this loss here, gives us here a lowest usable frequency. Due to attenuation during daylight, if the sun was shining from this side here. This was night, in the shade of the Earth. The sun coming from here was illuminating this part, generating all the time new electrons in the D and E layers. This attenuation adds loof. Loof is not a fixed figure. Move is a fixed figure. Move depends exactly on the geometry, so the altitude of the ionospheric layer and its plasma frequency. While loof, lowest usable frequency, it's also a function of our transmitter power. If I have a high transmitter power, I can overcome this loss. So what happens during daylight? Here during daylight, day, say, loof during daylight is maybe in the range of 7 megahertz. Depends now on how you define it. Loof, the lowest usable frequency, goes to 0 during night. During night, these low layers with high amounts of neutral ions that cause collisions, they disappear. So I have no such attenuation at night. Lowest usable frequency here goes to 0. So it's frequent if I am using these effects in the ionosphere. Frequently I have to change the frequencies of my radios during day and night. And if you have a radio broadcast on HF, during the day broadcast stations used higher frequencies. During night they use lower frequencies. Not just HF, high frequencies, but also medium frequencies, medium waves during night, because even long waves even 100 kilohertz, because this loop goes down to 0, all the way down to 0 during night. Almost to 0, at least what is useful for radio waves. So this is in short terms what happens with radio waves. I should also understand here, maybe I forgot to tell you this thing here, this detail. So if the frequency is higher than the plasma frequencies, I have a dielectric with a relative epsilon. If the frequency is less than the plasma frequency, of course, I have a negative value under the square root here. I get an imaginary n. What does that mean? It means that this is a conductor that has some kind of conductivity gamma. I see that I only have a dielectric in the ionosphere when the frequency is high enough. Above the plasma frequencies, below the plasma frequencies, I have conduction. But before I get to this conduction, I already have in mind, because this is not now exactly defined layer. Here the concentration of electrons slowly grows and then falls back again. So if I have a conductor here, I may have a dielectric here. Or I have a conductor here, I may have a dielectric here. So before I reach the conduction inside here, I could also have reflection of a conductor. I could achieve this result. If I transmit vertically, I have no refraction in the ionosphere. I may have back reflection down to the ground when I am below the plasma frequency. But usually this in radio contacts does not count really much. In radio contacts, mainly I have refraction before I get to the conductive layer inside the ionosphere. Something I could further tell about the ionosphere. These things, it seems from these equations that the ionosphere is useless above 40 megahertz. Or maybe on particularly days with particularly active sign, when this thing goes to 100 or 200 megahertz, that may happen. Rarely, but it happens. It does not happen anything at higher frequencies. Yes, it does happen. There is a small variation of the refractive index even at higher frequencies. Say for GPS that works at a frequency of 1.5 gigahertz, I do have a very small, this is quite close to 1, but this epsilon is not equal to 1. I still have a small refraction, and this small refraction yields me during the day errors of approximately 100 meters, up to 100 meters. While at night, I have no such errors due to the ionosphere. And I have special means to compensate for these errors in GPS. But even GPS working in the gigahertz range, these small changes in the refractive index, they do change the refractive index. It is approximate 1, but it's not exactly equal to 1. So it changes the distance measured, and since the distance is 20,000 kilometers to a GPS satellite, that 100 meters makes quite easily. So it makes quite large mistakes here. One final word about the ionosphere. We could talk the whole year just about the ionosphere. The ionosphere is a very complex matter. I only have 1 hour left here. In the Earth, I have some magnetic field. B0 of the Earth, or H0, is around 40 amps per meter. What does this Earth magnetic field cause? It causes electrons to circle this field. So electrons follow a circular or a helical path around the field lines. And what is now this frequency? This omega of gyromagnetic resonance, omega g, is now proportional to the charge of the particle proportional to the size of the magnetic field, and it's of the opposite sign. It's inversely proportional to the mass. So Q of electron, mass of electrons are involved. So the gyroscopic resonant frequency, gyro resonance frequency, is omega gyroscopic divided by 2 pi. In the Earth atmosphere, plugging in this number, this is around 1.4 megahertz. These things has many effects. It causes birefringence even for GPS. And even unreciprocal, so this is Faraday rotation. Rotation causes. But it also causes additional loss. Loss increases very much at this gyromagnetic resonant frequencies. And what is there, the background of all this? Now it's no longer being used, but 1.4 megahertz many years ago was a radio broadcast frequency band. And the whole medium wave broadcast is in the frequency range 540 kilohertz to 1605 kilohertz. Now we have this gyromagnetic resonance in this frequency range. We have much increased loss here. So medium waves at night with a very lowest frequency span very large distances. So if you have one of these old receivers, maybe a vacuum tube receivers with your grandmother or your grandfather, you can turn it on at night, it becomes alive. It hears stations from all over the world, but not at all frequencies, not around 1.4 megahertz. That's the reason, because of this loss, that 1.4 megahertz was used for local transmitters. Because they had no range, because this gyromagnetic resonance happens also at night. It's always there, making troubles. Was used for local transmitters, and what is left of that, the name is left. The name is left like Val 202. This was 202 meters. This is 1.4 megahertz. Local transmitters used these frequencies because they were not intended for international broadcasts thousands of kilometers away. And local transmitters, the name is still left here. The name we are still using today, though most people do not know what Val 202 means, really. It means 202 meters of wavelength, 200 meters of wavelength, and that's the reason local transmitters were built on these frequencies, with just the local coverage without using the ionosphere, because of the very high loss of the gyromagnetic resonance in the ionosphere. So this is just for fun, what I'm telling you. Okay, next time we are going to see other effects on radio waves. We can calculate everything in radio waves, but things are changing. The ionosphere is changing, the thunderstorms are changing, many things are changing. We have to look at fading and the statistics of signal fading in radio links. Starting with the ionosphere, of course, it was first observed in the ionosphere because of the changing solar activity of changing day and night. We will have to see how to handle these things mathematically next time. That's all for today.